Good afternoon. This is CIVE 634, Surface Water Hydrology, and today is class number 52, 052, for the fifth week and the second class of the week. The subject today is Overland Flow, and this could be a difficult subject, very mathematical, and it could also be I think it could also be fun, and I've done a lot of work in overland flow, beginning with my contribution in 1986, when I, for the first time, calculated the diffusion wave modeling of catchment dynamics. So I'll get into that story a little bit later on today. Okay, so today we're going to cover, I think, a whole lot of material. A lot of it is mathematical, so bear with me. Hold on to your seat, as I said before. We'll start with overland flow, and this is part of my book. Then we'll go into the paper that I wrote with Cordero Brana and Hassanin, and I'll tell a story about summer Hassanin at that time. We'll do a calculation with a computer, within the calculator, the online calculator, and so on and so forth, and hopefully we can finish the subject today. But if we don't, we'll leave maybe a couple of items to start beginning next week. So we start with overland flow, and I am not going to go into detail on this. It will take 4 weeks for us to examine in detail everything I'm going to say today. So bear with me. You're supposed to read this part of my book because you don't have enough background at this point. So rather than jump all the way to Hassanin's paper, which covers this subject, I thought I would just briefly, maybe take 10-15 minutes to discuss the basics of overland flow. One thing I'm going to say, though, is that in 1985, when I decided to write a book on hydrology, I had to do some planning. And the issue was, should I cover in detail overland flow or not? And the answer was yes, because I already done it. I was very conversant in overland flow, having just finished the 1986 paper, which was written in 1985, and I had done a lot of work in the early 80s, very basic work, fundamental work. So I decided to write this section 4.2 of overland flow, which tells the story of overland flow. It's a little bit advanced for a beginning book in hydrology. I thought my book was always beginning book. But suffice it to say that at this point, I decided to do this, and I wrote this section, which I'm going to now present briefly to you, the content of what's in there. I should mention at this point that chapter 4 of my book covers hydrology or surface hydrology of small catchments, that is, small watersheds. And section 4.1 is all about the rational method, which since 1889 has been considered the de facto method to calculate urban hydrology. Overland flow is relatively new. Remember, rational method, 1889. Overland flow began to be applied in the middle 60s with the work of Wooding and Woolhiser, and I'll have a chance to talk about Woolhiser a little more in detail later on. But let me just say at this point that overland flow is the calculation, the precise and very detailed calculation of how water flows over land. That is a very difficult subject, as Woolhiser in his 1995 paper was able to elaborate. And this, the Woolhiser paper is a paper that we're going to be reviewing at the end of this class, hopefully, if we get there. So overland flow theory. This subject of the plane, the overland flow plane, was developed in 1965 by Wooding. I believe it was in Australia. Yes, Wooding in Australia. And since then, other people did it here in the United States at the same time that Wooding in Australia. Woolhiser was working here at, I believe it was at, Woolhiser was at Cornell University. And there was another gentleman whose name I don't remember right now that was doing the same kind of work at Princeton. Shackey was his name. Shackey was doing his doctoral dissertation at Princeton. So all these three gentlemen contribute toward the middle 60s to the calculation of overland flow. All three of them use kinematic model, the kinematic model. And we now realize by this time that there are three models that we could use: kinematic, diffusion, and dynamic. And I'll have a chance to get back into that subject later on. That's one of my favorite, I guess you could say, subjects that defines Professor Ponce more than anything else. The classification between surface flow in kinematic, diffusion, and dynamic. Those of you that have taken computational hydraulics with me last year must know this subject already, hopefully very well. So flow over the plain, we have this characteristic which is very depictive of what's going on. We have the rainfall excess, and the response of the basin is a hydrograph because it starts from the beginning to respond. It doesn't wait until all the water gets through. When all the water is getting through the basin, it already reaches a peak over here. And then when the rainfall stops, then it starts receding. So this is the volume of rainfall, and this is the volume of runoff or response. And as you can see, there's a phase toward the right because there has to be some time for the water to get from the furthest, most remote part of the watershed to the mouth. There's different types of calculations for overland flow. The ones that are now being done have to do with numerical analysis. And this is part of what is as part of the details of the HMS model, which I'm sure many of you have already heard, if not already used. The Army Corps of Engineers HMS, Hydrologic Modeling System Model, developed or put out in the year 1998. So it's been 24 years since that model has been out. That model was a successor to the HEC1 model, which appeared in 1968. So 68 to 98, HEC1, 98 to 2022, the HMS model. That's the standard for hydrologic calculations in the United States, and why not say it throughout the world? The Army Corps of Engineers models are used throughout the world. So for us to use these models, and we're often kind of a chance to do that, we have to know something about overland flow, right? Otherwise, we would be blind. So this is what I'm going to be talking about here today in the last 15 minutes, because that's all we've got. We got the equations, equation of continuity and equation of motion. There's 3 ways or 4 ways to calculate the overland flow. The storage concept, which was pioneered by Horton in the 1930s, and then the kinematic, diffusion, and dynamic technique. The storage concept, I said Horton, 1935. Kinematic wave technique, that was the technique that the gentleman in Australia, Wooding, as well as Woolheiser and Shockey of Princeton were using around the 1960s. At about the same time, at the end of 1960, Chow out of Illinois had one of his students do a PhD on dynamic wave technique. They actually did it. It's amazing, the dynamic wave technique. And the reason will be apparent later on as I get into more detail as to why I'm a little bit chuckling here, saying they actually did the dynamic wave technique. They kind of jumped over from kinematic to dynamic without going to diffusion because they obviously didn't know. Then in 1986, I came out and did the diffusion wave technique for overland flow. And then, of course, later on, everybody decided, and this is a story that I should tell, and I will eventually, of how the dynamic wave technique is unnecessary, totally unnecessary for overland flow. I'll get there. So diffusion wave technique turns out to be the best. And it's only circumstantial that your professor was the one at the center of developing the diffusion wave technique. I don't have the time in this course to look at all the details of how this happened, both as well as the advancement of numerical analysis and progress in that field, as well as the need to go beyond the kinematic wave technique into the diffusion wave technique. But first is, historically speaking, the storage concept. And the storage concept is due to Horton, like I said, in the 30s. And this system, it's nice, and we did a paper in 1997, but it's kind of old. I do not believe, I think we should study it because it's part of history, and also it helps us to understand the process. But when it comes down to doing the calculation, the only thing we could do is use HMS, or use some other alternative model that other federal agencies, US agencies, or else European agencies. The Europeans have a model that they call she like a woman. but it's not called she because of a woman, but because she, for the French word système hydrologique European. I don't know French, so I can't pronounce it. But as the letters of the acronym is for System Hydrologic European, the she model, has been around in the process of development and improvement for at least 30 years. I can tell you stories about the she model, but I'm not going to do it at this point. We'll have to wait until later on if we have time. So we have the time of concentrations, and you would recall that I have already talked about time of concentration, and we have a formula here that came out from overland flow theory, which is very similar to the ones that have been developed by, for instance, Papadakis and Kazan. And Papadakis and Kazan knew the theory, but they were not about to get into the theory. What they did was they collected a whole lot of data, and then they correlated the data, and they came up with a formula that looks pretty much like this, in which they, of course, empirically define the value of M, which is the exponent of the rating, the exponent of the discharge area rating. So we also have to distinguish the overland flow case for laminar as opposed to turbulent, and perhaps in the middle between laminar and turbulent, because Horton said in his studies in the middle 30s that he had determined the value of M for many of his data. A lot of his data, M came up as 2, and he knew very well at the time that 5/3 was turbulent and 3 was laminar. So he figured out that 2 must have been in the middle, and he was correct, somewhere between laminar and turbulent. Why? Because laminar flow is when you have very, very thin flow, and turbulent, very thick. And what about if it's in the middle? And most of the calculations, according to Gordon, in the field were coming out with values of M equal 2. So that's how we represent the roughness or the regime of the surface flow. So as you can see, all this stuff is kind of in tune with what we have already said. Another thing is that what friction to use in overland flow, and the answer is we need to use a number which we call N capital that resembles Manning's N, but it is not Manning's N because it considers flow that is not turbulent but rather laminar, and or rather in between turbulent and laminar. So for that purpose, we artificially jack up or increase the number of N, lowercase n to be uppercase N, and as you can see, these numbers go all the way to 0.8. And I did talk about this. We have some experience with this. One day I was in Florida with Florida water engineers from the Florida Water Management District, and they said they were using a Manning's N, or this N, the capital N of 1. And I said, boy, really, that's beyond my book. And they stood by their numbers. They said that's what it was. And I believe them because I had not done the calculation. I had no way of arguing with them on whether it was 0.8 or 1. It doesn't really matter because at that point, it could be either one or the other. So we have in here the integration that was done both by Horton as well as by Izzard. Izzard was a gentleman that was working in the 1930s and 40s in drainage of airports. And he also analyzed the equations of motion and came up with these formulas, which are fairly complex. And I'll come back later on to show this again in a more consistent fashion. So we have overland flow based on kinematic wave theory, which was started by Woolhiser and Wooding, as I already said. We also have a kinematic wave solution over here, which is basically the work that, again, Wooding and Woolhiser did, and as well as Shockey too. All these three gentlemen did their work at about the same time in the middle 60s. Their publications mention that or make that clear. They were working at about the same time. I can't really tell you who was the one to publish. It doesn't matter because if one of them preceded the others, it would have been like a month or two, and that is pretty too small to even consider. Those three people were advancing these ideas in the mid-60s in various U.S. institutions, academic institutions, as well as in Australia. And then Wooding's open book, right? That is still used. And there is an issue of whether this is realistic. I have read the paper by, I'm laughing because I've just read the paper by Woolhiser, and that's one of the questions that he poses. Is the open book realistic or not? And we have a story on that. I'll get back to refer to that story later on. applicability of kinematic waves. The issue of, are kinematic waves good for this calculation? And the answer is, well, Woolhiser had the same question, and that he developed the kinematic flow number, which he said should be used to test the applicability of any wave, because the wave size determines whether the flow is going to be kinematic. Later on, though, we found out, myself, through the so-called S-curve, the study that I call the S-curve 1977, that it was not the length of the wave, but rather the relative length of the wave in reference to the amount of friction, which was an L sub O, by the way. And those of you that have studied perhaps a little bit my S-curve would relate to what I just had said. Okay, so the kinematic shock is another story. The kinematic wave has a tendency to steepen because of the properties of the equations. They are nonlinear, and therefore the kinematic shock is there. This is a story that, or rather a situation which caused a lot of thinking. Woolhiser and many of the other people that were working with him at the time. So why do they steepen? They steepen because they're nonlinear. Why do the kinematic shock appear so much in the numerical model and not so much in the real world? That's the very good answer. It would take 30 minutes for me to explain why. But let me just say at this point, because the open book was a simplification. And since it was a simplification, it had no diffusion, because diffusion means complexity. Irregularities lead to diffusion. So if you have a plane that is very regular, then you can develop very easily the kinematic shock in that plane. While if there's irregularities in the real world, the kinematic shock is not going to develop. Does the kinematic shock develop? Yes, it does. And it leads to the so-called killer wave in reality. But that's another story that we will talk about later on. Comparison of storage and kinematic wave solutions. I'm going to get there today with the Hassanin paper, so let me just skip that. Diffusion wave theory is what we developed in the year 1986. We decided that the kinematic wave theory was not quite correct. Even though Woolheiser was my professor, he had an office right next to mine at Colorado State back in the early and mid 70s. And I had chatted a whole lot over coffee with Dave Woolheiser. He was a proponent of the kinematic wave, but he realized, and he did say that he was a very honest man. He said that it was imperfect. So we decided to come up with a diffusion wave, and ours is better. I'm not going to say it's perfect because nothing's perfect, but ours is better than the kinematic wave. And there are also very many stories related to the improvement of the kinematic wave by the diffusion wave. I'll get back to that later on. Okay, so I finish in here at this point, and I'm going to go to this paper by Ponce, Cordero Braña, and Hassanin. Cordero Braña was a mathematician, and I ran into a snag because I'm an engineer. I've done mathematics, extensive mathematics, and I can do it. But if I can ask a mathematician to do it for me, it's better. So I asked Professor Cordero Braña to do the math. And that was well done. And then I had Hassanin, Summer Hassanin, as a student at the time, 1997. Summer Hassanin. I'm not sure if it's Sumner or Summer. I really, honestly, it's been how many years? 25 years, right? Summer Hassanin wrote this paper. Well, we put it together. Typically, when I write a paper with a student, it's a 50-50 proposition. I have them do the work, the basic work, the legwork, so to speak, and then I kind of analyze it, and I know it. And now I am telling you off the bat that I could do the work at the time, particularly at the time, perhaps not now, but at the time I could do the work by myself. But that was not the call. I needed to get the students involved so that they would learn also. So Summer learned a lot by writing this paper, and then we polished it and published it in one of the journals. I believe it was the Journal of Hydrology. But the interesting thing about that, a couple of stories, is that Summer went on to work with the city of San Diego. And I have a friend out there that was recently employed to work directly under Summer. He's one of our students, graduated in the year 2014. So he's been out for 8 years. And he now works directly, in other words, Summer Hassanin is his supervisor at the city. So I asked him this morning, I said, she's your supervisor, what is her title? And he said that there were two divisions within the department, and that she was head of one division, the planning division within storm drainage. So I guess you could say, or anybody could say, that in 25 years, Summer rose to become head of that division. And she is in charge of maybe 60 to 70 people out there, professionals working in the, as I said, drainage, planning division of drainage. I haven't seen Summer in a whole lot of years. One of these days, our paths will cross again. And there's a story in Summer that I will come back to talk later on. So at this point, what I'm going to do is I am going to get into the calculator, because we have a calculator just about anything. Anything that can be calculated within reason, we have a calculator. So we have a calculator of the conceptual dimensionless overland flow hydrographs. Calculator. This is our calculator. Okay, I didn't put any data in here because I'm going to wing it in here so as to show you the results. I should tell you at this point that we have all the formulas: linear, Chesi, Manning, Horton, and Izzard. And over here, linear is m equal 1, Chesi 3/2, Manning 5/3, Horton 2, and Izzard 3. What's m? M is the rating exponent. Remember I said earlier that Horton said that m was 2. It was not 5/3, but it was 2. So it led to the calculation by Horton, as well as us, of this rising limb. That's the rising limb of the overland flow hydrograph. And this one's the receding limb, okay? So we're going to come over here, and then we're going to do this calculation. I should tell you at this point, for your information, that before we've had this calculator for about maybe 5 years. No, 7 years. It was in the year 15 that we developed this calculator. I had a student, I don't remember her name right now, but working with us. She got a degree with us in the year 2016. So in the 15, we did this calculator. August 18, we published this calculator. It's a great calculator. Now, the thing about this is that prior to me doing this calculator, I would ask the students, the grad students, namely people like you, to do the calculation by hand. But then when the calculator came about, then I don't do that anymore. So you have been spared the calculation by hand of the hyperbolic tangents of the Horton equation. You know, that's kind of involved. But I used to do it though. When we started doing this 30 years ago, we would have the students, we had no qualms about asking the students into getting into the hyperbolic tangent equations, which were kind of a little bit sticky, if we can say that. But at any rate, now it's out of your hair. We have the Watershed sample here, and select units US customary. We're going to use all formulas, rising, receding, both rising and receding. Say the length in feet, say 200 feet, the slope 0.01. These are typical numbers. Effective rainfall in inches per hour, say 1 inch per hour. That's cool. That's a lot of water, by the way. Manning's coefficient 0.04. That's good. The water temperature is usually in SI customary, 68 degrees, or let's say 70 degrees, rounding the number. And we do the calculation and we get all the hydrographs in here. Rising limb of formula linear, receding limb of linear, Chesi formula m equals 3/2, receding Chesi, Manning's formula, receding Manning, Horton formula, receding Horton, and finally Izzard formula, receding Izzard. So we got everything in here. All the formulas that I'm going to show you in a minute here, where they were, how they were calculated. And as you can see, 1 second, it took 1 second. We can't, we got to realize that now we have the techniques, and we can no longer resort to the old techniques. Doing it by hand would be inappropriate at this point. You could do it if you wanted to, but I'm not going to ask you to do it. So that's the practice of this formula here. And now I'm going to go back, and I am going to show the paper by Cordero Braña and Hassening to show briefly the equations. I'm mostly interested in the equations. This is generalized conceptual modeling. So it's a generalized, yes, for everything. It applies everywhere. It's dimensionless. Once it is dimensionless, it is generalized. It can be used all over the world. This is mechanics. Technically, it is mechanics. Conceptual mechanics, but still mechanics. Remember, we talked about that already. So it's deterministic method, and it has a little bit of conceptual in there because it has some conceptual components into the deterministic method. Okay? So, and we decided to put in one graph all 5 formulas that had not been done. Gordon had done his formula, Izzard had done his formula, other people had done the other formulas, but nobody, to my knowledge, at the time, and we did this in the year 1997, original version, 1997, there it is. That's the original paper. So the original version, where am I? Here, yeah. That was it. So we did the calculation, we have the conceptual model. This is in a way repetition of what we had already done in the book in different ways. It looks very much the same actually. The solutions, the solution of the Horton equation, which is over here. And you can see for m equal 1, it's easy. For m equal 3/2, that is the Chesi formula. Then 5/3 gets really complicated. Then m equal 2, m equal 3, and so forth. M equal 1, and so forth. By the way, I should tell you that when we did this with Bhavya was her name, Bhavya Bhupalapati, she was a lady from India. She did this calculation and we tested and we did the model. The idea was to develop the model, the computational model. And we had a bug. We had a bug in the original paper. And therefore, we had to correct it. And I do believe, let me check this. This is interesting that we should check this. Let me just check. Maybe it's not here. We'll see. No, I'm sorry to say that it's not here. I don't know. I'm going to have to double check that and make sure. But we had to correct the original paper by adding an addendum because there was a bug. You know, so many equations. Anybody can make a mistake. So we made a mistake and we had to fix it. Okay, so let's go back in here. Back in here, I think. Yeah, I'm getting lost in here in my own work. Okay, so this is the end of that paper on the calculations for the 5 curves that were done by Hassanin and us. All 3 of us were working together on this. And so we published this paper and we really got a lot of credit for it. It's a nice piece of work. Look at this work over here. And then we subsequently put it on the web because we decided several years ago, about 3 or 4 years ago, that we were going to put everything on the web, on HTML. I love HTML. I think it's very, very powerful. Thanks to our friend Tim Berners-Lee, that in 1993 developed the so-called protocol HTML that allowed him to talk to every computer in the world. And that led to what we now call the web. So we decided to put these papers that were black and white on the web in color. And we, of course, did that over a period of 2 or 3 years. I had students involved in doing this kind of work. What we need to do is to scan the papers and then clean them up and make sure that there are no errors and so forth. But we did that, and we're in the process of doing all our papers on HTML now. We believe that the print version is passé, it's old, it's black and white anyway, it doesn't have any color. So imagine who of you are out there are watching black and white TV. And not really. Only if you're watching Ken Burns' video, by the way, it would be black and white because at the time that Ken Burns is representing the 20s and 30s, there was no color TV at the time or colored movies. Color movies came about in the 30s and 40s and perhaps even they were already established by the 50s, I think. I wouldn't know completely because I wasn't really active at that time. But this is the paper that we reproduced in HTML format on the web. And we have patterns to do this, so we can do this kind of work readily. We have a format, and we follow our format, and we're fine. Okay, so that's as far as the Cordero, Brania, and Hassanin. So now, the story of water does not flow uphill. I put this today on the web to give you a little bit of fun in here. So I'm going to show you this video. Can everybody see the video now?
1997, I wrote a paper which generalized the classical Horton-Izard conceptual model of overland flow for rating exponents in the range 1 to 3. The results were based on the integration of several complex mathematical functions.
This figure here shows the most extensive experimental watershed that the U.S. has been able to put together in Arizona, next to Walnut Gulch, which is next the Walnut Gulch ARS. ARS stands for Agricultural Research Service. You know that already. Walnut Gulch Experimental Watershed near Tombstone, Arizona. You may recall that Tombstone, Arizona is famous for the shootout at the OK Corral. I believe it was 1905 or 1909 at Tombstone. So I visited Tombstone a couple times over the last 20, 30 years, and they have programs out there to show you where this happened, and a story, a tourist attraction. The shootout at the OK Corral, which is right, I believe, I'm not exactly sure where exactly is Tombstone, somewhere in here. You can match it with a map and check it out. But this is the experimental watershed, is the most instrumented experimental watershed, I believe, in the world. Where, by the way, Woolhiser, our friend and Professor Woolhiser, spent some of his professional time. By the way, I should mention to you, in case you have not figured this out, that all these equations, how terrible they look, they're all already in the calculator. You don't have to do them again.
Our first attempt was to use existing software, but we soon realized that something was wrong. The outflow hydrograph was not as expected. The water was actually flowing uphill.
While we're at it, I should mention something I had neglected before without really wanting. These are all diffusive hydrographs. Diffusion means they have some diffusion in there. All of them have some diffusion. Diffusion shows as spreading, as attenuation of the peaks. And therefore, all these 5 hydrographs can be considered diffusive hydrographs. Which one is the most diffusive? It appears that m equal 1, which is linear, starts very quick in here because it's linear, it's kind of odd, okay? Starts very quick, but then it becomes the most diffusive. And the least diffusive would be m equal 3, which is the Izard formula. By the way, now I recall talking about Mr. Izard. I actually met the old man maybe 30 years ago at a conference. None other than Izard. Yeah, he probably won't remember me, and he probably passed away later on. He was almost 90, 95 at the time. But he was the Izard that developed this equation. Okay, so in here we have 5 diffusion models. Let's not say waves. Diffusion models of the overland flow rising hydrograph. And over here we have a model that is not diffusive. And this is the kinematic wave. And the diffusion models, all of them consider at about this place at 1, at T star, which is the dimensionless time. At 1, they more or less approach 90%. We consider that is the time of equilibrium. If you could consider a certain time of equilibrium for these diffusion models. But the kinematic wave we show in our book, and we can go back to our book, mathematically, that the time of equilibrium of the kinematic wave turns out to be 1/2 of the time of equilibrium of all the other diffusion waves. About 1/2. Right here, we have 1 over here. So the kinematic wave turns out to be the fastest response because it has no diffusion. The kinematic wave has no diffusion. There could be no response faster than the kinematic wave. This is the fastest. And don't forget that the issue of fastness in here is represented in dimensionless form. That means in general, for all the applications, all over the world. This is mathematics, physics. Every system has to respond. There's no element of empiricism in here. It's all conceptual, deterministic. Okay, so the kinematic wave then is a fastest response. Now, Woolhiser, for reasons that will be apparent later on, because we're going to review his paper later on today, zeroed on the kinematic wave. But he was always a little bit doubtful about it because it was a lot of too much or very much an approximation to the diffusion wave, which was a little better. All of us that know this very well for more than 30 or 40 years understand that. The diffusion wave has to be better than the kinematic wave. Why? Because the kinematic wave neglects 3 terms, leaves 2 and neglects the other 3. Neglects outright. Well, the diffusion wave neglects only 2 terms and leaves the other 3. So diffusion waves got to be better. On that same vein, we could say that the dynamic wave is better because the dynamic wave does not neglect anything. And that has led many people to argue precisely this. Hey, let's use the dynamic wave because it's the one that is really the true one. But Professor Ponce has shown that the dynamic wave does not exist. Why it does not exist? Because it's in the middle of the spectrum where it's subject to extreme diffusion. In other words, the dynamic wave, the kinematic wave is over here, the diffusion wave is over here, and the dynamic wave, if we were able to plot this, it would be out here somewhere at the bottom. And since it's at the bottom, it doesn't produce a flood. If it does not produce a flood, then it's no interest to us. We're trying to calculate floods. We're flood engineers. We don't want to calculate a situation where there's no flood, right? We want to protect the public against the floods. And if there are no floods, there's no reason to protect, right? So as you can see, by analyzing these relationships, we are able to understand what exactly is going out there in the real world.
I told my co-author, graduate student Sumner Hassaning, there is something wrong with this solution. Water does not flow uphill. I instructed her to start from basic principles, to integrate the functions by parts, and to develop the correct mathematical solution for this problem. 2 weeks later, Sumner came back with the answer to the puzzle. The software that we were using had an error. A minus sign had inadvertently been changed.
By the way, the software that we were using, this is true. There is nothing to say or to convince us that all software out there has no errors. Software always has some errors. So we have to be wary and careful about all the software that we use as we learn the hard way in here.
To a plus sign.
Well, let me repeat that.
And
because
has inadvertently been changed to a plus sign. Once we placed the minus sign where it belonged, the solution behaved as expected, correctly depicting the rising limb of typical overland flow hydrographs. Thus, the moral of the story, if you're solving a physical problem, it behooves you to have some knowledge of the physics. Otherwise, you will be unable to assess the accuracy of the calculated results.
How was I going to take the original summary results that said that the water was moving uphill? No way. I knew the water was moving downhill. You see how it works? Okay, where are we now here? There we go. Uh-oh, we messed up in here. We cut it all out. I'm sorry. I gotta go back now. Okay, so I'm going to go back now. I have to. I got confused over there. Bear with me a minute here. Oh boy. Surface water, syllabus. So we're done with water does not flow uphill. So now we're gonna go. Okay, what are you guys seeing now? let me just,
We don't see anything.
let me go in here and I will go over, I believe I'm over here now, right. Okay, good. What do you see now? A green page, right?
Yes.
Okay. So, next in our reading is this paper, Parking Lot Storage Modeling Using Diffusion Waves, which I wrote in the year 1999 with Amy Bundy. Now, Amy was a grad student in the department back in the late 1990s. And she came over to me at the beginning and she said, Professor Ponce, I want to do a thesis. I believe she did a thesis. I'm not sure. I think it was not a thesis. It was a special study. You know how we get special studies done with the students. This was before the actual practice. That practice of the students required to do special studies is only about 10, 15 years old. But the work of Amy Bundy precedes that. It was in 1999. That was 23 years ago. But Amy, I believe, came to me and said, Professor Ponce, I want to do some research with you. And I said, well, you know, we got these subjects, and she chose this subject. I said, I have a model that works really well. That was our 1986 model of Overland Flow using diffusion waves. And I said, if you can apply it to practical situations and test it under various conditions, that would be a topic that could be published in a journal. So she did that. And it was the first time that extensive hydrographs calculated by the diffusion wave model had been done. Why is that? We wrote this paper in 1986 and we let it sit for 13 years, and that's the answer. We didn't have a student, or we were busy. You know, we're always busy. We're doing other things and we didn't pay too much attention to this. But the record shows that 13 years later, I asked Amy to do this work. I gave her the parameters. You're going to do this, you're going to do that. And she did it, and she did it very correctly and wrote the paper, and we put it together. And this is the paper that myself and Amy Bundy put together. And we published it in ASCE. It's called Parking Lot Storage Modeling Using Diffusion Waves. The idea was a bit far-fetched, if you want me to categorize it at this point. Far-fetched because what we wanted to do was to use the parking lots, or to be able to use a parking lot as a storage element, so that it would reduce the amount of flooding downstream. I mean, does this make sense? And the answer is yes. Everybody in the field knows that if you retain the water upstream, it doesn't flood downstream. That goes without saying. Because if you don't retain it, it moves downstream and it floods because it accumulates one with the other and eventually creates a huge flood. So the idea was to use parking lots to detain the stream. Little, well designed, it could be done. And to this day, I think that it could be done. The problem is that it's not just a technical problem, it's a social problem. People want the parking lot to be drained immediately because they've been used to that for 30 years. Drainage has been like that. Drain the parking lot immediately. Right after it rains, you know, within reasonable time, 5 minutes, and the water is gone, dry. And that's the way they designed it. They put a 2%, 1 or 2, I think it's 2%. They put 2% storage, or rather slope, to the parking lot in the design by grading it, and therefore the 2% is a kinematic flow, and kinematic flow is the fastest flow. I already told you that. So they remove the water, and they create a flood downstream. But of course, it doesn't matter, it's somebody else's property. But if you look at the whole thing, and this is where Summer comes in with her knowledge, because she's head of the planning division of the city of San Diego stormwater department. She should be handling these things. I should talk to Summer about this, because I believe that this could be done within reason. It could be done. Unfortunately, if it's going to be done, it will take 20 years or more to not only to change the grade, to change the new concept, not the old concept. You're not going to go out there and change the parking lots to Professor Ponce's design. No way. But you could do that in the future for new construction. It could be done. But to my knowledge, it hasn't been done. So what we have in here is a theoretical practice of showing that this could be done. And the reason why we did this is twofold. First, because we thought that it should be done, or it could be done perhaps in the future. And second, because we wanted to test the model. We wanted to make sure that we knew this model was good, and therefore it needed to be tested. Why were we so sure that this model was good? Those of you that have taken computational hydraulics from me last year may maybe remember that I said that our diffusion wave model of catchment dynamics was grid independent. Do you remember that? Grid independence? That's a very fancy word. That means the results don't vary with the grid size. Every one of these models has a grid size. You got to design the grid size, put it in there. But not, this is the only model in out there that could claim to be grid independent, because this is based on diffusion wave, not on kinematic waves. The kinematic waves are all grid dependent. So if you have a change on grid, or you double the grid, or half the grid, the answer will be somewhat different, maybe 5, 10%, which means that you don't know which one is the answer, because it depends on the grid. So in order to get into grid independence, you have to do what I did back in the year 1986. I did the Overland Flow modeling, but I did not use the kinematic wave. I used the diffusion wave concept using a method that had been developed in 1979 by Conge out of France. And I met Conge in the year 1980 personally at Colorado State. And I was talking to my wife this morning. Remember, I said Conge, and we met Conge. And Conge is, John Conge, I believe, is still alive. She's in the late 80s, beginning 90s. But I'm going to check again, because if he passed away, I probably would learn about it. But at any rate, with the formulas of Conge, which were great formulas, of which we benefit a whole lot, we were able to put this model that was grid independent. And since this was grid independent, I totally was 100% behind, totally 100% behind it. And we came up with these. We varied the storm type, and we varied the equilibrium flows, and you have to get into detail. My point in here is not to overwhelm you with all the stuff, just to show you that this stuff could be done, and it is part of the hydrology of surface water. So we came up with these calculations. We varied the storm type, storms type 1, parking lot A, parking lot B, parking lot C, parking lot D, and we varied the slope from 1%, 0.5%, 0.2%, and 0.1%. Why these slopes? Because we felt that 1% was kinematic, for sure. 1 and 2% kinematic slopes. We know that for a fact. 0.5%, we have a lot of experience with this. And we know what's kinematic and what's diffusive, or what diffusion. 0.5%, it's in the midst of it, in the middle. 0.2% maybe less, but 0.1% definitely somewhat diffusive. Somewhat diffusive. Because diffusion wave, the capability for the wave to become diffusive, or the flow to become diffusive, depends on the slope. If the slope is mild, the diffusion gets in, or creeps in, so to speak. So we use these 4 slopes, and we were able to come up with these calculations. This one in particular, for instance, is very good, and I use this as a show-off of this. This one over here is the slope of 0.1% that did not reach the maximum. It stopped there because the rainfall stopped. And over here, 1% was kinematic. If it wasn't kinematic, it's very little diffusion over here. So this is little diffusion, a little more diffusion, and a lot of diffusion, which allowed the hydrograph to be subconcentrated. Remember the concept, subconcentrated? The hydrograph is subconcentrated already. The issue of whether subconcentrated flow exists or not has been settled by Sherman in the year 1935. He said, I cannot use the rational method because it gives me too big answers. The answers are too large. I need to use something more in tune with the mildness of the watershed, because he was using large watersheds that were on the order of 2,000 to 5,000 square miles. And so he developed the unit hydrograph, which we will cover later on in more detail. Standard method in watershed analysis. So these charts in here demonstrate beyond doubt, I would say beyond reasonable doubt, beyond doubt, period, that in fact what these calculations show, that you can indeed calculate diffusion waves within a numerical context and apply them to watersheds. So with that, then, we finish that paper, and now we come to the Woolheiser paper. And this is a fascinating paper. I reread it this morning. I reread this paper every time I teach this class. So I must have read this paper maybe 10 times, completely. It's full of detail. Who is Woolhiser? Well, let's take a look at what he says. Let me see if I can get a little bit bigger in here. I'm greatly honored to be named the Hunter Rouse Lecturer for 1994 and to join the highly distinguished group of previous recipients. So Hunter Rouse was 1994 lecturer. Hunter Rouse, I'm sorry, not Hunter Rouse. Woolhiser was the Hunter Rouse lecturer 1994. You would recall, not you, the people over in the other class, 638, would recall that we talked about J.F. Kennedy being the Hunter Rouse lecturer, I believe, for 1983. So we're not familiar. Our group is not unfamiliar with the Hunter Rouse lecturer. So the Hunter Rouse lecture is an ASCE prize that is given to very important people which have a strong record of accomplishment in their respective fields. Kennedy was a hydraulician. This guy is also in hydraulics, by the way. It's hard to define. When you talk about routing, you cannot say I'm a hydraulic engineer or hydrologic engineer, because routing is in the middle of both. It's like me, Professor Ponce. Are you a hydraulic engineer? And I said, well, depends on how you define it. I do actually both. Why? Because I'm sitting in the middle, which is routing. Okay? Woolhiser claims he was never a student of Hunter Rouse. In the late 70s, Hunter Rouse spent the summers in Fort Collins where he taught a graduate course. I actually missed that course because he started teaching in 1977. And in 1977, I was already a doctor and I was already teaching over there at Colorado State. So I didn't go to Hunter Rouse's class. I am told by friends of mine that it was fun and it was good and so forth, very instructive. But Hunter then subsequently retired in Arizona, and by now I think he's probably, no, he has to be. At the time he was 70, 75, and now it's been what? 50 years, so he's dead, long time, okay? I am struck by the large element of chance involved in receiving an award such as this. Clearly, the factors that condition the probability relate to my good fortune. So Woolhiser is also talking about his good fortune in having outstanding teachers, students, and colleagues, and being in the right place at the right time. That is very important. Otherwise, it cannot be done. Okay? Much of my career. Now, this gentleman is going to do a history of his own career and get into much detail later on. We will skip the details. I'm interested in the history and the reason why he wrote this paper. That's more important for us. Because don't forget, this guy worked on this subject for 40 years. And then after 40 years, he had done so much work and it was high reputation that he was asked to comment on it. And he did. And he did it very candidly, by the way. I should tell you at this point, interestingly, that Professor Ponce is always at the right time at the right place. And I was in Spain at the time because I had been invited to give a lecture. And for one reason or other, I ended up going to Cordoba because we wanted to visit. My wife and I wanted to visit Cordoba. The Mesquite of Cordoba, something like this, everybody wanted to see. I ran into Cordoba and we happened to be at the University of Cordoba. And who did I think I ran into? Woolhiser. He was, unbeknownst to me, he was out there working. And in this paper, he says that he was in 1994, he was in Cordoba. So I'm not lying. I met actually Woolhiser, whom I knew from my time at Colorado State. And he told me at the time that he had written this paper, he was writing this paper. So this paper has a lot of emotion for me because I was actually talking to the author at the time. Interestingly, though, when he was in Spain, he read about El Dorado, which was an issue that had to do in Latin America and South America. El Dorado, you may have heard of. It's a fable, a myth, or something like that. But he does say that clearly in here. One of the books that I read during my stay in Cordoba was The Loss of El Dorado, a most interesting book in which the author describes some 16th century Spanish expedition to search for El Dorado. There's an ample stack of books on El Dorado. Nevertheless, this morning I went on the Amazon and I bought this book. I wanted to see what Woolhiser at the time was referring to. I figured that Naipaul was from Trinidad. So he is one of the gentlemen originally from Indian extraction that came to Trinidad 100, 150 years ago when the British were out there in control. They brought all these people from India. So this gentleman wrote a book on the loss of El Dorado. El Dorado is essentially a Spanish delusion. There had been a golden man in what is now Colombia. Colombia with an O, by the way. He made a mistake. People make that mistake between Colombia and Colombia. Colombia, the country. It was in Colombia. A chief who once a year rolled in turpentine was covered in gold, but the tribe of the golden man had been conquered a generation before Columbus came to the New World, and there was a lot of fighting everywhere, as it is today too, by the way. So Indian memory that the Spanish pursued, and the memory was confused with legend. Okay, so this is, he says, this is far from a perfect analogy. But why is Woolhiser bringing up the subject of this book that he wrote while he was in Spain? Because he wanted to make a case that perhaps the pursuit of the calculation of overland flow was a hydrologic El Dorado. And that's exactly what he calls his paper, a hydrologic El Dorado. You see where he's coming from? Are we searching for something that is unattainable? So Professor Ponce spent an hour already telling you where all the equations are and how the calculators and everything that we have already done. And now I'm talking about what Woolhiser said in 1995. He says, is this attainable or unattainable? Can we do this or not? And no person better than him to talk about this, because he had started his work at Cornell in the middle 60s. So he was 30 years into the practice when he was asked to write this paper. And he had worked those 30 years, and he talks about this in here. The entire 30 years he's working on this subject because he was a federal government employee and he had that choice. Federal government told him, you know, Dave, you're going to be working this for 10 years or 20 years. He was with ARS, and these scientists stick to a topic and they don't move out of it. As a matter of fact, Woolhiser is a very good example of that. And he's talking about it very candidly. Okay, so he was working for 30 years. And he tells the story, and I will get into the story because I think it's fascinating. The story of how he started his work at Cornell with none other than Professor Liggett, who, by the way, was another one of the recipients, an earlier recipient, I believe, of the Hunter Rouse lecture. Okay, he says, my attitudes are clearly colored by my interest, past research assignments, and experience. So it is appropriate that I summarize them. He was working in Arizona, Wisconsin, Missouri, Iowa, and Colorado. And he finally, the last part of our career was spent at Colorado State as part of the ARS delegation working at the Engineering Research Center at Colorado. So I interacted with Dave extensively over coffee while I was at Colorado, because we were working in the same floor for 3 years while I was a student there. And as well as when I was a professor, because I spent 3 years as a student at Colorado and then 4 years as a professor, because I moved from student to professor out there. And all the while I was visiting every once in a while with Dave Woolhiser. Not so much with Roger Smith. And those of you that, yes, that's right. In this class, I talked about Roger Smith. Roger Smith was working with Woolhiser, was around there, but I didn't have a whole lot to talk, or could not talk, or did not talk with Roger as much as I talked with Dave. When I did my S-curve, I had such friendship with Dave that I gave him my paper to read, and he read it and complimented me on it. I'm not exactly sure how much time he took on it, but he did compliment me on it because it was a good paper. So he goes into some definitions. He's very detailed because he shows the experience that he had. Very detailed on what he knows and what he doesn't know. He's very humble in telling you what he doesn't know. But this is the point that he's trying to make, and he makes it really well. He says, in order to do the modeling, we need to make some simplifications. Per force, we have to. The open book is a simplification already. You don't see an open book out there, and yet we use it all the time. So the question was how bad of a simplification it is, and the answer is, don't worry about it. It's a simplification. It's not perfect, but it's the only thing you could do. Given all things considered, it's the only thing we could do. Otherwise, it would be almost impossible to do. So he basically comes up with the conclusion throughout the paper that he has to do it because that's just the only way we can do it, and that we must do it because we cannot cross our hands and say, no, we can't do it. Let's go back to the way we did it 100 years ago when we didn't have any computers. Now we have the computers. So we cannot rely only on the rational method, which is 3 calculations. The Aguilar calculation that I'm going to show you hopefully here in a few minutes probably has 30, 40 million calculations in 2 seconds. So we have the computers, we got to use them. It's better. Now, what is my feeling on this whole thing? My feeling on this whole thing is that there's a what-if situation. You can use the model for what-if situations. You can say, what if the rain doubles? What if the infiltration reduces? What if the change is here, this change, that change? We can run 15, 20 cases of what if in no time. Well, we could not do that with the older models. They did not have that capability to do what the models, the numerical models can do when you pose the question of what if. So it's a better solution. Sensitivity of the model to errors can also be studied very much. Plus, we got the computers. We paid for the computers. And this is kind of cynic for me to do that, to say that at this time, but it is correct and real. We got the computers and we got to work with the computers. And it is also, it gives us a lot of, how can I say, we are proud that we can do this calculation with that detail, even though some of it may not be quite correct. I didn't say that. Woolheiser said that, and none other better than him to say that, who had practiced 30 years in this field. I've also practiced in this field, but I've practiced in several other fields, like 5 or 10 fields. Woolheiser only practiced in this field for 30 years. So I'm going to say that he knows more about it, more detail about it than myself. So the background, and in here he's got a statement that is really amazing, that I very much relate to. He's talking about how he developed his expertise, okay? And that's not of much interest to us at this point. Okay, here we go. Much of the research in the 60s, I'm over here right now, dealt with the mathematical description of overland and open channel flow. And investigators usually started with one-dimensional Saint-Venant equations or a simplification such as the kinematic wave. One-dimensional. Why one-dimensional? Why they didn't go to two-dimensional? Because we couldn't do it. The computer, we started using the computer in the 1960s. The first computer I used was in 1965 in Peru. And they had already been using the computer for 10 years here in the United States. But developing the computer doesn't mean applying it to hydrology. So it was the gentlemen such as Shackey and Woolhiser and Wooding that applied this methodology with the computer, with the computational digital computer for the first time in 1965. For the first time. What are they talking about? The computers of the time had, I lived through that, by the way. I'm old enough to have lived through that. The first computer had 7K of memory. The computer that I used in my dissertation, which was in 1976, had 76K of memory, the largest computer of the world. Right now, the computers that are being sold now, your cell phone, which already is a computer, has 32 gigs. So we go from kilo to megs and to gigs. So that's 1 million more times storage as well as speed and everything else. Okay, so we've improved a whole lot of stuff in the last 50 years, a little more than 50 years, exactly 57 years. I don't need to tell you all that, you know that. But let me say what he said. Actually, when Liggett and I, meaning Woolhiser, started our joint research at Cornell in 1964, we intended to show that the Saint-Venant equations, without simplification, were required for the overland flow problem, although we came to quite different conclusions. What happened was told to me by Woolhiser in 1995, because I met Woolhiser the next year over in Texas at a conference. And we're friends, you know, so we got together, we had some chatting, and we got to chatting and so forth. And he told me at the time, because I had already read the paper, and I said, oh, really? I didn't know this. And he says, yeah, Ponce, he said, I think he said Miguel. Yeah, Miguel, we were out there, and we basically Liggett, who was his professor, said to him, we're going to apply for the first time, because at the time people were doing that, the PhD people were doing that. For the first time, the complete Saint-Venant equations to the overland flow problem. That's what Liggett told him to do. And within a year, he went back to Liggett as a student. He was a young man at the time. He went back to Liggett and says, Liggett, I don't know how he treated Liggett, Professor Liggett or Jim. I also always call him Jim. Jim, he said, we can't do that. If I get stuck on this, I'll never graduate. And Liggett, who's a nice gentleman and understanding, realized that he had given Dave an insurmountable problem. So they downgraded at that point, and Dave told me this, they downgraded the model to be kinematic. They decided they could do the kinematic and I can graduate. And Liggett said, okay, fine. So they were the proponents, among the first proponents of the simplification of the kinematic wave because they could not handle the dynamic wave. Now the question is, why? That question needed to be answered, and it was answered by none other than Professor Ponce back in the year 1978 and 9. So it was done 13 years or 14 years after Woolheiser had his experience over at Cornell. We basically said that it was almost impossible to do the dynamic wave for various reasons, which I don't care to mention at this time. So that was the story, fascinating story. So he talks about the criticisms. There's always, like in the case of the curve number that I have talked about to you guys, there's always somebody doing the very fancy stuff and somebody trying to undermine and doing the simple stuff. And that's always like that, by the way. It happens everywhere, and this is not an exception. In here, Woolhiser is saying that there's people trying to do the very complex stuff and others that are trying to simplify it because they are claiming, right or wrong, that it is not good enough or that it is too much, too soon, too fast, right? Vevin, for instance, is a great gentleman, contributor in hydrology, originating in England. He's been writing papers for the last 50 years. I never met Vevin, but I've known of his work. I think we corresponded once or twice over the last 50 years. If there's an example, I believe, who said, oh, Liggett says this in 1990, look at this. If there's an example of a computational hydraulics problem that has been defeated by the wealth of detail, it must be this one. We are nowhere near to describing the hydraulic properties of a watershed. That was good in 1990 and is good in 2022. There have been useful advances in programs, but many of the watershed programs require the tuning of so many knobs that they are no better than statistical black boxes. The statistical black boxes are the stochastic statistic methods, which have to be considered of less caliber than the deterministic methods. We should not confuse one with the other, and yet Liggett is saying here that readily confused, take one taken for the other. That is not quite correct. Physically based models are not as accurate and are more likely to be misused as simpler models. Okay, I'm going to tell you my take at this point. I read this paper and I'm not going to bore you. I wish you and I urge you to read the whole paper because it's a good example of what has been done out there. But Woolhiser told the story in detail, very much detail. But my take on this whole thing is that there is room for simple models and there is room for complex models. And I do believe there's the user of simple models and the user of complex models. A user of simple models should not use a complex model because he or she wouldn't know how to do it. And a user of a complex model should not use the simple models because it would not be up to snuff, so to speak. So there's two divisions out there. The researchers are apt to use the complex models. The practitioners will go more for the simpler models. There's going to be somewhere in the middle that is claimed to be an advanced practitioner or a researcher that wants to come down to earth or so forth. There's always a transition in the middle. And I do believe that myself, I've tried to be in the transition, although sometimes my tendency is to get very sophisticated, as you probably have already figured that out. So that's my take, and I think that's what Woolhiser didn't say it quite, that there are two types of users. You cannot bundle all users into one category because that would not be correct. So finally, I'm going to go to the last page, not the last page, the previous page, over here. So analysis. Can the search of a physically based distributed model be described as El Dorado? I believe the answer depends on the scale, the scope, and the purpose. So he kind of didn't quite answer the question directly. Remember, this is Dave Woolhiser. He was writing this after 30 years of work in this specific field, in only one field. So we must treat his words with a lot of respect. We must always retain a certain degree of skepticism regarding the prediction of physically based models. How about that? And that of simpler model as well. So he basically, the same thing he said for the physically based complex models, mathematical models, of which I've talked about a lot today. And he also gives that criticism to the simple models. We must remember that new labor-saving techniques to obtain watershed descriptors, such as geographic information systems, cannot improve model accuracy if the model structure is badly distorted or if it is being applied at an inappropriate scale. He talks about scale, which is important. I talked about that in my book. And finally, let me say this, an example, a story. I have a few minutes in here. I was in Spain. I went to Spain several times in the early 90s. No, I was in Portugal, actually, not in Spain. Actually, Spain and Portugal are so close that I took the train and went to Portugal and visited some friends. I had a couple of students over there. That when I was at Colorado State, I was an advisor to a couple of the students. So they subsequently moved to Lisbon, and I was over there visiting, and they showed me a thesis that had been put together by one of the students over there, grad student. It was a PhD thesis. And the thesis was, as was normally the case, the application of GIS. The application of GIS. Everybody was applying GIS at that time. It was a new kid on the block. Everybody wanted to try it. But then they showed me the thesis, and the thesis was basically wrong, full of mistakes. So I basically had to tell them, you can't do that. Because no matter how good the tool is, if you don't know the subject, then you cannot use the tool. It's like trying to use a hammer where you can't find the wall. The same thing. Good example, by the way. I know how to use a hammer, but where's the wall? Okay, same thing in here. Okay, there's another example. I was in Brazil back in the middle 90s also. And a friend of mine who was also a student at the time, and he said, Professor Ponce, we have a thesis here. This gentleman has applied GIS for flood routing in a distributed context. I mean, that was my subject. So I looked at the thesis, I took to the hotel and I read it overnight, and I realized that he had made a mistake, a very big conceptual mistake. In his rush to apply GIS, he had forgotten to apply the 7 formula. His GIS was perfect, but he didn't know anything about flood routing, and he was routing floods. So I said to him, we had a meeting with his professor, and I said, you're using the Manning equation. And he said, oh, yeah, right, we use the Manning equation. Where else is there? And I said, no, when you're dealing with floods, flood waves, you got to use the 7 formula. Boy, he really had a surprise coming. He didn't know the 7 formula. He was so busy working on the GIS features of the model and so forth. And that could happen, by the way. You can get very much into the detail of the technology or the methodology and forget the basics. That, of course, is wrong, and it should not happen. So with that story, I am finishing up in here. And what I'm going to do is leave the last item, which is the, let me work in here. The last item is the thesis by Aguilar. But since this is a subject that will take more than a couple minutes that I have, I'm just going to stop there, and I'm going to leave it for the first thing that we do. It's only one subject. Let me just double hit in here. There it is. I'm only missing D13, which is a diffusion wave modeling it's an MS thesis by Aguilar, Rosa Aguilar, 2014, and then the application in the calculator. Okay, lecture 61 would be on Monday. Thank you. I'll see you next Monday.